So again, as we go through and look at these or work on these, you should be trying to get as much information down as you know first. Okay? And if you start to question stuff, that's okay. Okay? But when you're going through and doing nomenclature, it's going to be strictly multiple choice, so you can probably eliminate answers. Okay? So for this first one, we have cadmium. Okay? CN. Some of you might be going, well, you didn't ask me to memorize that. That's why I also said use your notes. Okay. CN is cyanide. Okay. How do we know that's a special one that we'd have to memorize? Well, I've got 3 elements listed. Okay. When we look at nomenclature, the only time we have 3 different elements is ternary ionic or ternary acid. Okay. If it's ternary ionic, that means a complex ion. That means you have more to memorize. Okay. So recognizing those patterns can help. We also have another case of a metal showing up, chromium versus cadmium. We write out the name for chromium, note we have the Roman numerals. Should I include the Roman numerals in cadmium? For those people I talk to, should you include the Roman numerals? No. Why do we not include the Roman numerals for cadmium, but we have to for chromium? The Roman numerals specify the charge. Well, cadmium has to be charged. Why am I not specifying it? I'm required to know that the charge on cadmium is always a +2. If it is always a +2, there's no point in writing it. Even if it's correct information, I shouldn't be writing it. And this is one of the things I also find kind of frustrating with nomenclature. I understand the value of it, but it's frustrating, particularly for students as well. Okay. If I wrote cadmium Roman numerals 2 cyanide, that is correct information, but I'm specifying more information than is minimally necessary to solve the answer, which then means I'm wrong. Okay. So you have to follow the rules. If you step outside of the rules with nomenclature, you are wrong, period. Okay. That's the way it works. Okay. The next one, 2 elements, so we're at least in binary. The next one's a little bit easier because carbon and oxygen are both nonmetals. So we don't have to worry about charges at all. We're immediately going into kind of our root systems or our Greek systems. I've got carbon. There's 3 of them, so I'll call it tricarbon. The oxygen is oxide. I changed the suffix on it because it was the second one in the list. There's 2 of them. Dioxide. So tricarbon dioxide. Next one, chromium. Sounds like people are getting excited about that one. Okay, so that means I'm assuming you got that right. Chromium is a CR. Oxide is that O. Okay, we now need to specify the amounts of each of those. Okay. The quick thing that students go through and do is they say, oh, well, it says Roman numeral 3, that must mean there's 3 of them. That is completely false. Okay. That 3 means the charge on chromium is a +3. What is the charge on the oxygen? -2. How do I know oxygen's a -2? That's one you were told to memorize. So when you encounter ionic compounds, you are told to memorize one of them because that's how you would figure out the name. If you didn't know the charges for either of them, you wouldn't be able to figure out the formulas. Okay. I don't know how many chromium, I don't know how many oxygen. But when I add them together, it had better equal 0. Okay. So at this stage, at least for the first half of today's lecture, it's always going to be 0. Okay. We're coming up with a neutral compound. So what could x and y be? Well, an infinite possibility. Okay. I want the smallest whole numbers that satisfy that, so I can go through and start taking guesses. Okay. Some of you may start to recognize patterns. Okay. What is a common multiple between 3 and 2? 6. Isn't 12 also? Yeah. Why is 6 better than 12? It's smaller. I'm looking for the smallest whole number multiple. How do I make 3 a 6? Multiply by 2. Guess what x is? How do I make this 2 a 6? Multiply by 3. Guess what y is? Now I have my correct formula. Okay? The other option, as the video elucidated, was just guessing at what x is, solve for y, see if you get a whole number. Both of those methods work. Okay? The last one, dinitrogen tetraoxide. We've got nitrogen, we've got oxygen. What is special about both nitrogen and oxygen? They're both nonmetals, which means the di means there's 2 nitrogens, the tetra means there's 4 oxygens, and I have my correct formula. How are we doing on nomenclature? Okay. The exact name or formula coming out of these is not critical in nomenclature, because on a multiple choice test you will probably be able to eliminate a bunch of answers, okay, and get through it. So I'm not super stressed about nomenclature itself as the end product. What I am stressed about is the process to get there. Okay? Balancing out those charges, that is super, super important. Knowing the charges, that is also super, super important. Okay? So you need to be able to think about how the name is coming together, but not necessarily get the name.
So in a multiple choice, you have to work all of it to find out which one is the balance.
So
Right.
if it was a multiple choice question, do you have to even come up with the exact name? It's not a bad idea, because then you say, well, this I know is the correct answer. Which of these matches that correct answer? That would work. These things I know to be true. Which of my answer choices have those true statements in them? Okay? There's a variety of ways that you can go through and approach an exam question. Okay? Most students are taught you have to know the answer. You don't have to know the answer on a multiple choice test. You just have to know which ones are wrong answers. Okay? And then potentially pick C, except you all know better than that, because what should you be doing?
A and B.
Read the directions. Read the directions, and you potentially have a hint to help you through that. Okay. Feel free to take a look at your exam 1 and see if it's always C.
I did. It's not.
Okay, so here's our quiz. What do we got? 1, 2, 3, 4, 5, 6, 7 reactions shown up here. Any 5. I don't care which 5 you pick. Pick any 5, and I want you to go through and tell me the reaction type. Predict, let's change that, because that's a lot of stuff to do. Give me the reaction type, predict the product, and balance the reaction for any, because that's 3 things, for any 2. Any 2 you want. As soon as you've got it done, go ahead and hold it up, and I'll come around and grab it. Little survey, we decided that 2 of those we wanted to look at. So reaction type, that first one is a combustion. How do we know it's a combustion? Okay. Couple big tip-offs. It's got oxygen. Okay. Just oxygen isn't going to help us out with combustion, because by definition, or combustion reaction also needs a carbon-hydrogen source. The other big tip-off that it's a combustion reaction. All combustion reactions produce water and CO2. Everything about that question or that equation screams combustion. Okay? How do you know all those bits of information? Well, that's why I have summary slides that go through and tell you what to look for each of those. Okay? So, predict the product. The product was already there, so I'm not going to predict that. And now balancing the reaction. Combustion reactions can be exceedingly tricky to go through and balance. Okay? And I believe this one is no exception. So when we go through to balance, we'll start with carbon. How many carbons on the left? 4. Carbons on the right? 1. The 2 only applies to the oxygen, not to the carbon. To get it to apply to the carbon, I would need parentheses, which aren't there, so I can't apply that to the carbon. Okay? So I have to make sure that I have 4 carbons. How do I make it 4? I'll change the coefficient in front. It's now 4. Okay? I'll now move to hydrogen. How many hydrogens on the left? 10 hydrogens on the right. 2. How can I make 2 equal to 10? I need a 5 in front. That becomes 10. So far, so good? I'm gonna assume that was a yes. Oxygen. How many oxygens on the left? Oxygens on the right. Well, there's 4 and 2, so there's 4 sets of CO2 molecules, which means I have 8. But oxygen also shows up in water. How many do I have on the right? I have 13. How do I make 2 an even number equal 13 an odd number? For those of you being like, you can't do that. You're right, you can't really do that. Okay? And so there's a couple options on how you could go through and do this. Okay? One option is say, yes, you can make 13 from 2. I would multiply 2 by 13 halves. What happens? The 2's cancel and I'd be left with 13. So yes, I can do this. Okay? The problem with that is I then have a fractional molecule. Am I allowed to have a fractional molecule? No. Okay? So the way I could eliminate that fraction is then multiply everything by 2 again. That means everything by 2, which means the number in front of the C4H10 becomes 2. The number in front of the O2 becomes 13. The number in front of CO2 becomes 8. The number in front of H2O becomes 10. Yeah, that looks okay, right? Everybody kind of see that? Some people are laughing at me, so I'm going to guess no. So how about we make it a little darker? Is that better? Yeah. Okay. So we did a lot of math there. That's a lot of changing things. That could very well mean everything is screwed up. So what should we do? Check it. So we go back through and we now get to reset. Carbons. How many carbons on the left? I've got the 4, but I have 2 multiples of that, which means 8. On the right, I just have the 8. Hydrogens on the right. You're like, I was looking at the left. I know. There's 2 and the 10. I got 20 hydrogens on the right. Hydrogens on the left. 10 and the 2. I've got 20. How many oxygens on, what do you want to do? The right? Okay, that's a hard one. Sure. We've got 2, but 8 sets of those, which means 16. Okay. This is why this question becomes difficult, because we can't even count on just our fingers. We have to take off our shoes. Okay. And you're like, that's mean. That's the truth, unfortunately. And I'm not saying that's your truth. I'm saying that's my truth and probably everybody's truth. How many oxygens coming from H2O? 10. How many oxygens on the right-hand side? 26. How many oxygens on the left-hand side? 2 and the 13 gets me 26. Did it balance? Yes. What should I do now? Check it again. Right? I don't want to check it again. I'm already mad enough at myself. Okay? Kind of makes sense? This is an exceptionally difficult one because of that fractional thing that comes in and messes with your brain. Okay? We don't like fractions. We have to work with them. Okay? Next one at the bottom. Sulfur solid reacts with oxygen gas to produce sulfur dioxide. We could theoretically just read the English and be like, I know that's this chemical reaction. I would make the argument that you don't know that right away, that all of the things that we've looked at have been evaluating the chemistry, so look at a chemical reaction first. Sulfur solid, well, sulfur has an S for a symbol. Solid is an S. Reacts with, there's that stupid of again, oxygen gas. There was a question about oxygen gas. Oxygen of and have no fear of means diatomic. Oxygen has to show up as O2. To produce sulfur dioxide. So sulfur And oxygen, the dye tells us that we have 2 oxygens, so we get sulfur dioxide. So, looking at this now, I started with 2 things and I end with 1. That looks like a combination reaction. So that reaction is indeed a combination reaction. I'm hoping that that didn't get recorded. It happens. The next question was predict the product. We didn't really have to predict the product, we just had to draw what was told. So this was another kind of cheat on us. We didn't have to do too much work there. Balance the reaction. Sulfur's on the left. 1, sulfur's on the right. 1, oxygen's on the left. 2, oxygen's on the right. 2, is it balanced? Yep. That's why I said that one was an easier one to go through and solve. Okay. Questions? Okay. Just for kind of future reference, I now know you have attempted all of these. Right? So I could be like, I wonder what kind of question I could put on an exam. I don't get it. Sorry if you don't get it. We're moving on. Decomposition reactions. Decomposition, you're ripping things apart. You start with 1 thing, you end with at least 2. Sometimes you can end with 3 or 4. But for the most part, it splits out into 2. Right? The rest of this slide goes through a variety of examples on how you could go through and do this. Okay? And believe it or not, I said we ended on a previous one, but we did end on this one because this was the equation. Actually, did I solve this one? I don't actually remember. I think I just told you guys to solve it, right? And I think I said that was going to be the quiz. Well, that was pretty stupid. Okay, sorry. I'm losing it, yeah. Sodium. What is that symbol? Na. Hydrogen? H. Carbonate? CO3. Okay, sodium hydrogen carbonate decompose into, so that means reaction arrow, and I'm now asking you to predict the products. But I don't expect you to predict products with decomposition reactions. How would you figure this out? How about you read the statement I also gave you, so you don't have to memorize it. Metal hydrogen carbonates decompose to give a metal carbonate, water and carbon dioxide. What is the metal in this equation? Sodium. So I want a metal carbonate. So sodium with carbonate. Okay. It's also going to produce H2O and CO2. I could now go through and attempt to balance this. Scanning through. We're going to notice it's not going to balance. Okay. For those of you who don't trust me, feel free to try this on your own time. Okay. You can try and balance each of those individual elements, and you'll notice you will continually loop. It will never balance. Nothing you can do about this equation is going to cause it to balance. It's going to get insanely frustrating. You're going to be like, well, I suck at balancing. No, you don't suck at balancing equations. What you suck at was predicting your products, which is really coming back to nomenclature. What is the charge on sodium? A +1. What is the charge on carbonate? -2. Is that formula correct? No. Those charges don't balance out. The product that you predicted was invalid, which then meant when you attempted to balance the equation, it's going to constantly cycle on you because you're trying to balance something that doesn't exist. Of course it's going to be problematic. Right? Balance that product first. So when we look at the rules for balancing, I always tell you, balance your products first. That means look at those and make sure they're correct. Okay? How do I make that formula correct? I need to make sure that when those two come together, they have 0 charge. I need 2 sodiums. The formula is Na2CO3. Now that formula is correct. Well, is the formula for water correct? Yes. Is the formula for carbon dioxide correct? Yes. Now I can attempt to balance the question or the whole equation. So we have to make sure that you check your formulas first before you initiate into a massive balancing process. Okay? Because balancing an equation is very frustrating if you don't have the proper things to balance with. Okay? If we now go through and attempt to balance this, sodium's on the left. 1, yep, sodium's on the right. 2, not balanced. How do I fix that? I need a 2 out front. Remember, balancing the equation, I have to change the coefficients. Okay? Hydrogens on the left. I see 1 in the formula, but there's 2. How many hydrogens on the right? Just 2. Oxygens, it is good. Oxygens on the left. There's 3, but the 2 applies backwards. I get 6. Oxygens on the right. I get 3 plus 1 plus 2, and I get a total of 6. Did the oxygens balance? Yes. Make sense? Okay. One of the things that I typically see students do is they see this work and they go, okay, this is how it's done. So they go through to balance and they write sodium, hydrogen, oxygen, and they write down what the initial numbers are for everything. And then they have to go through and start changing those numbers. Okay? When we solved this, I did not write sodium, hydrogen, and oxygen and write down all their initial numbers. What did I write down? Sodium. And I balanced sodium first. Then I moved to hydrogen and looked at what numbers came out of hydrogen. Then I moved to oxygen and looked at what numbers came out of oxygen. Okay? I'm not trying to look at everything first. I'm looking at one element and then moving through the list. Okay? It helps to improve accuracy in the solve and eliminate redundancy in your calculations. Okay? Kind of makes sense? So when you look at the textbook, they're going to do the same thing. They're trying to get you to go through stepwise, but the only thing they can put in the textbook is the final solution, which shows all of this work. They're doing it stepwise. Okay? We could do another one. Okay? Again, I don't really want to stress on this because I don't expect you to predict products. Okay? But let's take a look at this because it says metal oxide. Okay, so I want to know what the metal oxide is in this process. So calcium carbonate decomposes into a metal oxide and CO2. What is the metal? And maybe it's not obvious because we haven't written down the formula. Okay. What is the formula for calcium carbonate? CaCO3. What is the charge on carbonate? A -2. The charge on calcium? Good looking at the periodic table. Second column, +2. Those charges balance out. That would be our formula for our calcium carbonate. What is the metal? Calcium. So if I'm asking for what the oxide is, it's going to be calcium with oxygen. I want to again predict my product correctly. What is the charge on calcium? What is the charge on oxygen? -2. Is that formula correct? Yes. Make sense? A little bit. Good. Okay. Single replacement reactions. Okay. This is where we kind of throw all sorts of things at you. Okay. We're talking about active metals displacing other metals in a compound. That's the bulk category for single replacement. It does not have to be a metal to replace. But if I have a non-metal, what is it going to replace in a compound? A non-metal. Okay, so non-metals can exchange just as much as metals can. The metals just tend to be the more popular one to look at. Okay, so within this, we start with something in its elemental state. I react it with a compound. The metal species exchange locations. Okay? So if we go God, I can never remember to fix this freaking slide. So let's just ignore that statement and look at this one and see if this is the right thing. So what would I predict my products to be? What is zinc a metal or a non-metal? Metal. Okay. Is sulfur, or sorry, what's in the next compound? Let's try that. I see lead, and now people are going to be like sulfur because I said sulfur, and that's actually why I backed off of this. I would argue that it is not sulfur, it is sulfate. That is a complex ion. Okay. What's the metal? Sulfate or lead? Lead is my metal. Okay, which means when I go through to do the exchange, what happens? Lead now needs to be chilling by itself, and zinc now needs to pair up with the sulfate. Yeah? What is the charge on sulfate? A -2. How do you know that sulfate is a -2? You have to have that memorized. That goes back to our nomenclature system. What is the charge on zinc? +2. How do we know it's a +2? Zinc was one of those tricky ones that you have to have memorized. Zinc, cadmium, silver. Is the formula zinc sulfate a correct formula? Yes. Now that I've predicted my products correctly, I can now start to potentially evaluate a little bit more if I so desired, which unfortunately we do. Okay? So notice the zinc and the lead sulfate on the left-hand side of the equation have phases associated with them. Guess what needs to happen on the right-hand side? I also need to specify the phases. Remember the lead and the zinc did a 1-for-1 switch. If zinc started a solid, and then what does the lead need to end as? It will also end as a solid. Okay. What is the zinc sulfate going to be? This will likely be aqueous if we're following the patterns. Okay, so at this stage, that's what I want out of it. Okay, we could go through and balance it. This would be a lovely equation to balance because it is balanced. Oh, that's fun. Okay, kind of makes sense? The next question that comes with this, because you're like, well, that wasn't too bad. Predictions needed is in big capital bold letters here. Because the next question that kind of comes with this is, yes, I may have predicted that, but did it actually happen? What do you mean? I mean, if I take solid zinc and I put it in a solution with lead sulfate, do I actually see lead solid precipitate out? Okay. That means I'd have to do an experiment. I'd have to test that. It's been tested. Okay. There's now tables of data that can explain the reactivity differences between a bunch of different metals. That's the next layer on top of your single replacement reactions. Those tables are known as the activity series. The activity series discusses the ability for individual metals to be more or less reactive than each other. So if we again go back up to that equation, which of course is now all deleted, my lovely work. Right, it was lovely, wasn't it? Sure, thank you. And you know, everybody needs some positive reinforcement every so often. And there we go. I now want to decide, did that reaction occur? Well, here's my list of activity series. Should I look at lithium? Why not? It's not in the equation. It's not relevant. Potassium. Okay, so you get the idea. We need to look for zinc and lead. There they are. Okay, well, zinc is more active than lead. What does that mean? Okay. Those people that have processed through and have potentially picked up the chemistry behind this might be able to draw the conclusion. The rest of us might be a little bit in the dark. Okay? Our activity, there's a couple ways we can look at it. The more active our metal, okay, it wants to be with something else. The more active you are, so if you're an introvert, okay, how active would you say you are? You're like, I'm not going to talk, I'm an introvert. Okay, fair enough. Let's try it the other way around. You're an extrovert. How active are you? You're pretty active. You're out talking with people, interacting with people. Okay? Extroverts. How happy are you to just sit at home all by yourself? Not very. You're an extrovert. Come on, share. Right? You don't like that. You want to be around other people. Activity is effectively a ranking of extroverted versus introverted. The more active you are, the more extroverted you are, which means put me with people. The less active you are, don't put me with people. So now I'm going to look at the equation. Okay? I want to use that information and align it back with the equation. Okay? Zinc is more active. It wants to be with people, or more so than lead does. Looking at the equation, where is zinc with other things? It's over here. Right? So we looked at it as the extrovert. Let's look at it as the introvert. Lead doesn't want to be with people. Where is lead away from other things? So if I now mix zinc solid with lead sulfate into a single solution, what happens? Well, the products happen. That means a reaction occurred. That's all it is. Okay? So we have to interpret an activity series. Okay? So we would have to know that lithium is the most active, followed by potassium, calcium, sodium, magnesium, aluminum, zinc, chromium, iron, nickel, tin, lead, hydrogen, copper, mercury, silver, platinum, gold. Which would be really awesome if I could have spewed that all out without staring at it. Okay? Why can I not spew it out without staring at it? I haven't memorized it. How many of you think that you should memorize that? Good. Okay? Don't memorize it. You're expected to use it. Okay? How would you use it on the homework? Flip the page in the textbook that lists it. I conveniently deleted the table name. Sorry. Okay, but it's in the textbook. Okay? On the exam, if you take a look at the first page of even your exam 1, you will notice I have a modified activity series. Okay? Because I don't want to list all of them. I list maybe 4 or 5, maybe 10. I don't know. Some number. You're expected to use it. Right? Which sets us up with some practice. Do it. Last one. So the first one, the only reason I'm looking at it is because I actually wrote most of the work up here. So someone went through, noticed the metals. They exchanged the metals. Okay? When we write out and predict our products, I don't write NO3 2. I just write NO3. Well, but you might be saying, well, isn't there a 2 over here? Yes. Why is the 2 written on the reactant side? Why do I have that 2 on the reactant side? That 2 is there so that nitrate balances nickel. That's why I have a 2 there. If I bring that 2 across, well, what was the meaning of the 2? The 2 was so nitrate balances nickel. Why are you bringing the 2 across? Typically, the reason most students are bringing it across is because, well, it was over here. Why was it there? To balance nickel. Is nitrate with nickel anymore? No. That 2 can't be there. Okay? And this is kind of a weird statement. Okay? That green 2, because I've got it circled in green, cannot be there. Because the green 2 was necessary to balance nickel. It's not with nickel anymore. It can't be there. Sorry. That was a bit dramatic. I hate it when I delete all my work. Sometimes it's recoverable. That's not. Okay. So, what I had written underneath, though, was the charges. We know magnesium's a +2. We know nitrate's a -1. Because magnesium's a +2, group 2. Nitrate we know is a -1 because we memorized it. Is that formula correct? No. No. to make sure that formula is correct, what do I need? I need 2 nitrates. So I'll put my parentheses in the 2 to make sure this is MgNO3, 2, not MgNO32, right? Okay. I have that 2, right? Didn't I just say I'm not allowed to put that 2 there?
Yeah.
Not true. That is not what I said. What did I say I was not allowed to put there? The green 2. And you're like, oh, fancy you with your colors. Those 2's mean entirely different things. The green 2 means nitrate balances nickel. What does the blue 2 mean? Nitrate balances magnesium. Okay. I still need that 2 there, but it has an entirely different meaning than the 2 appearing in the exact apparent location on the reactant side. So be careful transferring subscripts across. Okay? That 2 should not necessarily come across. It did here, but for reasons of balancing your formula. But I brought the 3 as a subscript across, didn't I? Did I challenge that at all? No, well, why not? Why is the 3 there? So you might say, well, the 3 is there so oxygen balances nitrogen. What is the charge on nitrogen? -3. Good, you memorized that. Oxygen. -2. Are those charges balanced in nitrate? No. When do you have to memorize charge? Or apply charge? Ionic compounds. Is nitrogen a metal? Is oxygen a metal? Are there charges with nitrogen and oxygen? No. Okay? That's why I have to memorize the charge on nitrate is a -1. So again, why the 3 now? Okay? If I get rid of the 3, is it nitrate? No. If I get rid of the I in nickel, is that nickel? No. The 3 is as much a part of the name or symbol of nitrate as the I is part of nickel. Okay? So our numbers show up as identifiers for that compound. They also show up as amounts. And we get this weird crossover between them. Okay? You have to recognize when it's an identifier and when it's a number. Okay? That comes from memorizing your complex ions. That's why I told you to memorize them. Okay? Kind of makes sense? The next question that could come out of this is, did this reaction occur? Well, I find my nickel. I find my, what's the other one? Magnesium. Magnesium is more active, so it's the bigger extrovert. It wants to be with other things. Where's magnesium in my equation with other things? In the product. Which means if I take these 2 things and I mix them with each other, what happens? It makes product. This reaction is a valid reaction. Let's take a look at the last one. Gold with copper sulfate. Okay, this becomes a very tricky one, because how many of you know the charge on gold? You're like, I wasn't told to memorize it. Yeah, I know. You weren't. If you encounter an equation where you aren't told to memorize the charge, assume it stays the same as whatever started with. Why? So it's easier to balance. Okay? It's completely silly and ridiculous and dumb. Okay? That's why we shouldn't ask that question explicitly. Okay? So I'm going to make the statement that gold is going to be a +2 so that sulfate and gold balance out easier. Okay? Horrible statement to make, but I don't have any better context for that. Okay? I'll now go back and use the same rules that I used for the magnesium and the nickel nitrate. I need to find gold and copper in my activity series. Where are gold and copper in the activity series? Well, gold, right there at the bottom. Copper, pretty close to the bottom. Okay? Copper, being more of an extrovert, wants to be with something. Where is copper with something? In this equation. On the reactant side, this is copper with something. If we look at copper in the products, it's by itself, right? Okay. So if I mix these 2 together, what happens? Copper says, I'm happy exactly where I am. Does a reaction occur? No. Okay. Which is an interesting observation. If I take gold and I mix it with any metal, what happens? Nothing. What do we use as our currency? Copper and no, come on. What actually supports our currency as is? And don't tell me pieces of paper. Gold. The world's currency is based off of gold. If you have a bunch of gold, then theoretically you can print more money. If you don't have a bunch of gold, when you print more money, what happens to the value of the money? It goes down. And you have to print even more money, and the money becomes worth less than the paper it was printed on. Okay? So, why did we pick gold as our standard of currency? Let's flip it. Let's pick lithium. Okay? Now what happens? Okay? Federal Reserve with all the gold in it, right? Okay? All I got to do is somehow break in and just throw water balloons at it that happen to have zinc ion in them. Those of you being like, yeah, good luck breaking in. Okay, I just make sure it rains. I drop a little hole in the top of the building, okay, that allows rain to trickle through.
My question is, how do you drop a hole?
Play Portal, you'll understand. Okay. We get a hole where now all we have to do is attack the Federal Reserve with water guns and water balloons. What happens to the gold or the lithium when the water hits it? It dissolves, turns into a liquid. What do liquids do? They move. Any drain in that facility, and what happens? You've now lost all of your standard of currency. Lithium is a horrible metal to use. Okay? Some of us have jewelry, right? Okay? And if it's more expensive jewelry, what jewelry do we use? What metal do we use? Gold. What else do we use? Platinum, if we have a lot more money. Or silver. Where are silver, platinum, and gold? All at the bottom. What happens if you used copper jewelry or nickel jewelry? Some people are laughing. Maybe you know that experience. What happens? It turns you green. The metal is now active enough that it reacts with your skin, leaving behind metal ions that are colored. We pick gold, platinum, and silver because they are now so low in activity that they don't react with our skin and they stay gold and our skin stays skin colored. Okay? So we can use chemistry activity series to decide what our monetary units should be. Arguably, it was the other way around. We're like, well, why are we using this? Oh, chemistry. Okay? Kind of makes sense? The next part I want to address within this. Let's take a look just at the copper sulfate and what happens to copper through this equation. What is the charge on copper in copper sulfate?
2.
Okay? It ends up being a +2. That's not something I memorized. How did I know it was a +2? We could jump to the periodic table. You're not told to memorize the charge on copper, so tough. You are required to know, however, the charge on sulfate. The charge on sulfate is -2. If there's one copper and one sulfate, the copper must be a +2 to balance that sulfate. What is the charge on copper in the product? Okay. I'm hearing a +2. Where do we see charge written? In the top right. Take a look in the upper right for copper. What do you see? Nothing written. What is the charge on copper in your product? 0. Our copper started at a +2 and went to a 0. Who cares? Those are just numbers. How did we change the charge? Okay. I started positive and I went to 0. I decreased the charge. Well, what things determine charge? Electrons. To go from a +2 to a 0, what did I do? I added 2 electrons. Copper gained 2 electrons. Anybody see in that equation electrons? I don't remember what the symbol was for electrons. You should. We were tested on that. That's the E, the minus sign. Does anybody see E minus sign? No. And yet, electrons somehow changed positions. Ooh. That is now chapter 17 in our oxidation states. Okay? Active metals, don't worry about it. Okay? This is that video. Sorry, my back is broken. We were talking about reduction and oxidation and ultimately oxidation state. When we go through and look at our chemical reactions, there are some chemical reactions where our quote-unquote charge appears to change for individual elements. It typically happens for our metals, but it doesn't have to be our metals. Okay? And it turns out that what we've been calling charge is horribly wrong. Charge applies to a bulk unit. If I'm looking at a single element, I actually want to refer not to its charge, but to its oxidation state. The oxidation state is the balance of protons and electrons for an element or an atom. Charge is the balance of protons and electrons for a larger unit. Could that unit be an atom? Yes. And that's where the confusion comes into play. Because people go through and say, well, the charge and the oxidation state are the same thing for, say, calcium. Because if I look at calcium, in the upper right-hand corner, there's nothing written. So that means calcium must be a 0, which is true. It is a 0 charge. It is also a 0 oxidation state. The charge is always given to you in the upper right-hand corner. The oxidation state is something that you must solve for. When I move over to the calcium in the product, you might say, well, how would I figure that out? Because the charge is, again, 0 written in the upper right-hand corner. The charge is written on the unit. The unit here is calcium hydroxide. To determine the oxidation state, I have to break apart the unit into the individual elements that made it. If it is an ionic compound, I'm allowed to split it into the ions outright. And what I'm looking at is calcium plus 2 and hydroxide minus 1. What is the charge now on our calcium? A plus 2. What is its oxidation state? It's also a plus 2. This is where we go through and say, well, the charge and the oxidation state are the same. They aren't. Okay? They're applying to different things. They're related, but they're not the same. Okay? So, our oxidation state rules, ionic compounds, you have to know those charges. Oxygen will always have a minus 2. The next one, the sum of your oxidation numbers equals the charge on the unit. That's this fancy formula here. For those of you that happen to remember the formula that I told you to use for nomenclature, guess what? It's pretty much the same thing. Except the only thing that I modified is instead of saying charge in each of those boxes, I've now specified oxidation state. Because it is an oxidation state. When you were calculating it in nomenclature, that was oxidation state, not charge. Okay? So your unit can be a molecule or a compound, and that's where this stuff becomes tricky. Our definitions, again, charge is always specified in the upper right-hand corner and applies to whatever unit I'm looking at. So for this first one, the charge is 0, plus 2, minus 1, minus 2. To solve for the oxidation state, I have to go through and use this silly equation. Okay? You have to? Yes. Because if you go through and do this, you will then start to recognize where it becomes trivial. For that very first compound, how many elements are in that unit? 1. What is the oxidation state? I have to solve for it. I don't know what it is. It's X. Okay? Plus the number of the next element. How many other elements are there? None. So 0 times whatever, I don't really care, that disappears. What will this equal? The charge. What's the charge on this unit? A plus 2. What is the oxidation state for copper plus 2? Well, X equals plus 2. What happens if I move to, say, sulfate? Now things can potentially become a little bit trickier. Right? Can I ask the question, what is the oxidation state for sulfate? No, because oxidation state is for an element. Sulfate is not an element, it's a compound. How many sulfurs are in sulfate? 1. I don't know its oxidation state, X. Plus, how many oxygens? 4 times its oxidation state. I know that's -2 because that was a rule I was told to memorize. This then has to equal the charge, which for sulfate is -2. Now I can solve for X. X is +6. The oxidation state for sulfur in sulfate is +6. The oxidation state for oxygen in sulfur is -2. Right? Unfortunately, we're out of time for today. Where I will tell you that we will pick up, oh my gosh, skip all that, is looking at reactions, and now what does that mean to us?